That's why the title is mentioned as quantum inspired cloud computing. But most of you are belongs to different branch, right? How many of you are belongs to CSE branch? So majority is CS. Okay. So I will make my talk little bit general, and you can also use your mobile to write the code. Although there is lab setup is not there, okay, but you can write. I'll tell you that you can open a link, and in that link you can write a small code, so that you will understand that how actually quantum computing works. That's why the title which I have made here, programming quantum computers. So there are some misconceptions related to quantum computing. First, let us discuss that. You know, in current system we have central processing unit, or called as CPU. So when quantum computing is launched, we have quantum processing unit. Instead of saying central processing unit, we say quantum processing unit, or we call that as a QPU. So now the question arises that although quantum computers are not available to a common user, okay, it is not available to a common user, is QPU is going to replace the CPU. Okay, I am using two terms. One is QPU, that is quantum processing unit. Another is called as CPU, that you know already, right? So here, once quantum processor comes to reality, reality means it is already in reality, but once it is reached to a common user, is it going to replace the CPU? What is your idea about this question? Yes or no? Answer is yes. Okay, QPU is going to replace the CPU. Madam said yes. Any other answer? No. What my question? Try to understand my question. My question is that CPU is now independent, right? Without QPU, our CPU is working, right? All the computers are CPU. Once quantum computing will come into picture, let's say QPU is affordable with respect to cost, with respect to its usage and some everything. So is it going to replace the CPU? Okay, let us simplify this question. You have another term called as GPU, which we call as a graphical processing unit. So many computers are having GPU, like those people are specially interested in gaming, play games, or video editing or audio editing, writing a simple code in parallel programming, they need GPU. So when GPU come into picture, is it going to replace the CPU? No. In the similar manner, when QPU will come into picture, it is not going to replace the CPU. Okay, that is the fundamental idea you should think. Next, in what way QPU is advantageous? Why a CPU is not capable? Why we are going for CPU plus GPU? Why CPU plus GPU is not sufficient? That's why we are going for CPU plus QPU, or CPU plus GPU plus QPU. That you need to understand. To understand this one, let us revisit our computer architecture. You know, there is a person by John von Neumann. He proposed one architecture which is followed by modern computer system. What is that architecture? The architecture says that you have a input device, like our keyboard is considered as an input device, right? And we have a output device. I can consider monitor is a output device, or I can consider printer is a output device. In between this input and output, what we have? CPU. And if you go to the individual component of the CPU, what you have inside? What we have? We have CU, control unit, we have ALU, we have a memory unit, that's why people say MU. Now try to understand this one. What is the main job of a control unit? Different signals we are passing, right? Like if I want to read, or if I want to write, if I want to transfer, all these signals are controlled by CU. But who is performing this task? ALU. That's why it is called as arithmetic logic unit. Arithmetic logic unit do the most of the computation. So if you move from this John von Neumann architecture, based on that our CPU is there, right? If you go to GPU, GPU case ALU unit is more. ALU unit is more. What do you mean by ALU unit is more? Suppose I will ask you to add 100 numbers. So you will add 1 plus 2 plus 3 up to 100. Right? ALU will take care of this one. With the instruction of CU, ALU is going to execute that. Right? Now, if I have 4 ALU unit. So what I will do? I will divide this task into 4 parts. Okay? So mostly GPU is made for that one. If I divide a particular task into small subtasks, then each and every ALU part can take care of, let's say this is executing up to 25, next one is let's say 26 to let's say 50, next one is let's say 51 to let's say 75 or 76 to 100. So you can see here the time it is required to add 100 numbers by a single ALU unit is now divided by 4. It is reduced with a factor of 4 if you go for GPU. So whether it is a GPU or a QPU, you need CPU. CPU instruct the GPU to perform this particular task. So when we go for a quantum based computer system, CPU is only going to give instructions to the QPU to do. That's why this misconception should be avoided. QPU is not going to replace the CPU. Now, another misconception is that if I take a binary number system, all of you know binary number system is having 0 and 1, right? Binary number system is 0, 1, and in the previous lectures also you might have seen that quantum is able to store beyond this one, right? Not only 0, 1, we have superpositions, so we can store multiple things, right? So if you come to that example, input is always in 0, 1 format, right? If I ask write a program, finally the program is encoded into 0 and 1. Computer understand only 0, 1. So computer means I will give this take care of the CPU, right? Now CPU is going to instruct either GPU or QPU. In this case it is QPU, but earlier if you go to parallel system it is GPU. So QPU is going to take it in a superposition state. Superposition state means any value in between 0 to 1. You know, if I ask you how many real numbers are there in between 0 to 1, we have infinite values, right? So QPU will present it in a superposition state, any value in between 0 to 1. But finally QPU will again give the result to CPU, and CPU understand only 0 and 1 by the number system. So your input is in 0, 1 system, output is also in 0, 1 system. Between this input and output, CPU and QPU plays an important role. That's why the 0, 1 format is changed to a superposition state. Superposition state to we are again converting into 0 state and producing the output. So in terms of input output, we are not changing anything in quantum computer. Only in terms of computation, in terms of storage, all these cases we represent in the superposition case. That's why don't think that we will present in more storage, right? We will able to store more storage in superposition state. That is wrong. We are only representing it in the superposition state, so that number of possibilities is going to be increased, and finally we need to convert into 0 and 1, right? So now in this lecture, after a few introduction part, I will tell you about how to write program in a quantum computer, right? So for that you need not require quantum computer. There is a simulator that we are going to use, through which you can write the simple code, right? Like if I want to take a qubit, right? I will come to the concept of qubit, how to set a qubit, how to reset a qubit, how to apply a particular gate into the quantum, that we will discuss. So I will teach take these topics more or less, okay. If time permits, we will go for the multi-qubit. Otherwise, I will share the slide with Dr. Precious Madam. So Madam will share. Once you understand the single qubit, you can generalize into multiple qubit. But before going to one qubit, I will tell you some of the history behind this quantum computing. See, the term computing is not new. If you go for the term computing, Computing is not new. Computing is an old term. What do you mean by computing? Can anybody define what do you mean by a computing? You are doing early days, we are doing calculation in pen and paper. Now you want to perform the same task through a computer, right? So computing word is not new. It started with 1822. If you see the father of computer, which we call Charles Babbage, from there computing is started. And I have given a road map. You can see there are many computings are developed from 1822 to till date, and quantum computing is neither the first one nor the last one. But why we need these different type of computing? Can anybody tell? Why you need these computing paradigms? For faster processing, right? If storing, right? For that we need the processor. Yes, accurate results. Accurate results we are getting in all the system, but faster way we can get that particular result. Speed is important. Okay. So you can see early days in 1930 we have a mainframe computer. Mainframe computer is a very bigger computer, right? We have a lot of transistors, right? And chances of failing of that particular system is more. It is more frequently needs maintenance, right? Then people have come up with one of the computer called as ENIAC. That is called as electronic numeric integrator and computer, right? Okay, electronic numeric integrator computer. So ENIAC is called as the fast electronics computer. Okay, every phase of the computer we improve the speed of a computer system. So electronics devices incorporated in the year of 1945, but ENIAC computers store in the form of decimal values. You know decimal values, right? 0, 1, 2 up to 9. So computers store everything in the form of 0 to 9 in the case of ENIAC system. Then people started EDVAC, which is an extension of ENIAC computer. It is also an electronic computer, right? So they changed this decimal number system into binary number system. So from 1945 to till date, whatever computer is developed, they are based upon 0 and 1 only. Nobody has thought of changing 0, 1 into other states, right? Quantum also we are not changing. Quantum case also we are not changing. Just in the intermediate state, in order to do the faster computation, we represent it in a different state. But finally input output is in the binary number system. Then 1950 people come up with parallel computing. Quantum computing is an application of parallel computing only. We want to do the task parallelly. You take a quantum computer or you take a CPU or take a GPU, until unless you write sequential programming, the performance of the computer is not going to be changed. Okay? If I run this computer, if I do the sequential computation, nothing is going to be changed. In our curriculum also, you know, most of the thing what we are learning is only sequential computer, sequential programming. If you write a parallel program, just like you know in Java case we say multi-threading, right? Or you can see this case where I divided a task into 4 different subtasks, and if I want to run this subtask in different computer system, then computation is faster. That's why parallel computing came into picture. One of the popular programming is MPI, called as Message Passing Interface. MPI is used to write the parallel program. So without parallel program, you cannot use the ALUs that are present in the GPU, or you cannot utilize the component of GPU. Right? If you write sequential programming, even in Python programming also, general programming is sequential only. So try to write the parallel program to utilize the core or the thread that is present in the computer system. Otherwise, computer utilization is not going to increase, efficiency is not going to be increased. Once parallel computing, people have come up with other computing paradigms, like you can say cluster computing. Cluster is nothing but a group of computers. Like if you talk about a computer lab, in a computer lab we have 30-40 computer systems, and all these computer systems are more or less equal configurations because they are purchased at the same time from the same vendor. So when I combine such homogeneous nodes, because I call homogeneous because they are same type of structure, then cluster computing came into picture. So if I want more computation, as a single computer is not enough. I cannot run a single computer with a AI/ML code. Okay, so what I will do, instead of dependent on a single computer system, I will take a group of computer system. I will divide a task into subtasks, assign each and every subtask to one computer, then I will consolidate and produce the result. That is the concept started with cluster computing. But how many computers you will collect with the same configuration, same architecture, same configuration? It is not possible, right? In lab it is fine 40-50 computers, or if you talk about an organization, you may have 100 computers, 200 computers of the same configurations, right? But if you go for more than 1000 computers, 10,000 computer, 1 million computer, 1 billion computer, it is not possible. That's why people have come up with distributed computing. Okay, there also we can do the computation parallel. Distributed computing says that not necessarily the computer will be placed in one location, right? So there is a platform which is called as BOINC, that is called as Berkeley Open Infrastructure for Network Computing. It is by University of Berkeley, US. So this platform runs many voluntary projects, including weather forecasting. Okay, you know weather forecasting, right? Weather forecasting is giving us the information about weather of a particular location. So BOINC is really a distributed computing platform where none of the computer is owned by University of Berkeley. Only whenever your computer system is free, you can donate your resources to them. For example, I am not using my computer now, so I can simply connect and give the resources to BOINC. So whatever voluntary projects are running under the BOINC, okay, they will utilize the resources. So that is the birth of the distributed computing. And 1970 also people have started with the concept of quantum computing. Okay, you can see quantum computing started in 1970, but now after 55 years you can say we more focus on the quantum computing. Government also sanctioned a large amount to build the quantum computer, because we need faster communication, right? We need to reduce the computational speed from, let's say, 1 billion second to 10 second. For that, quantum computing plays an important role, right? Then after that also there are several computings are there. Just this highlights you what are the computing paradigms we are following for building the quantum computer. But behind all these technology, our objective is same: how to enhance the capacity of a computer system. Now, if I go to Google trend, see any topic you want to be introduced, you first check the trend whether people are interested in that particular technology or not. So if you go to Google trend, normally we search in Google tab, right, or Google bar. But if you go to Google trend will give you the information about what is the popularity of a particular word. You can also open your mobile phone if you want Google trend. In Google trend, once you open, if I type quantum computing and if I choose different filter, for example, these are nothing but the different filters we have, right? These are the different filters. So I have selected the filter as worldwide. I want to know that how many search queries are generated with respect to the quantum computing keyword as a search term. And I want to see the statistics from 2004 to present. That is the maximum period you can check the popularity of a word. So you can see, although 1970 I mentioned that quantum computing started, right? You can see out of 100, it is calculated out of 100, you can see it is more or less a straight line, right? But you can see after 2023, number of search queries related to quantum computer is increasing. What it says, it is now a popular technology among the people. How much we have contributed to quantum computing, that doesn't matter, but at least people have interest of learning this keyword quantum computing, right? That shows as per the Google trend. Similarly, Google trend also shows that the countries where maximum search query is generated, these are the 5 top countries, and in the 5th position there is a tie between our country and the country is Sri Lanka, where maximum search query is generated. Okay, in the first position you can find Ethiopia, then Ghana, Singapore, Canada, and the fifth one, Sri Lanka and India, is sharing the same index value. That means those people who are doing research work or related to these technologies, they are interested in this particular technology. That you can see from the Google Trend. Google Trend also provides you that what are the terms people are interested with respect to the quantum computing. Right? For example, those who are searching quantum computer, not only quantum computing related contents are coming, but also related contents are also coming, right? For example, here you can see some people are also, when they search quantum computing, quantum cloud computing is also coming. Why there is a need of cloud computing in association with quantum computing? That is more important. See, when I need a resource for a longer period of time, suppose I need to buy a computer for, let's say, next 5 years. I cannot go to a cafe, internet cafe or a computer cafe, use the computer. I need a computer for 24/7, okay, or let's say 12 hours per day, 12 into 7, and for a longer period of time. Then investing for buying a computer is better compared to go to a computer cafe and use the computer. So when the quantum computing is not available in the public domain means I cannot afford to purchase a computer. So the only solution is that the cloud can provide you that resources. Like you see, all of you are nowadays using Google Drive, you are using Google Mail, you are using Google Map, Google Photos. All these services are hosted where? In Google data center, which we call as cloud. Google data center manages everything. So if it is possible for Google to host a quantum computer, because Google is a very big company, they have a billions of profit, they can host, they can give these resources in rent basis, right? But as an individual or as an organization or this university, we don't have that much money to afford a computer system. That's why there is a integration of quantum computing with cloud computing. That's why you say that quantum inspired cloud computing, because until unless it is affordable, like I suppose if you go for a marriage party, you invited 500 people. I cannot buy 500 plates, right? Because after that party is over, that 500 plates of no use, right? Rather than what I will do, I will ask one person, a vendor, give me 500 plates for 2 days. In the similar way, I am asking some quantum computing resources for, let's say, 15 minutes or let's say 1 hour to use that particular service rather than owning that particular computer system. That's why you can see in the source query, quantum computing is associated with the cloud computing. Now, if you are really interested to work under the quantum computing, what are the areas you need to focus, that you need to understand? So for this, there is a hype cycle released by Gartner. Gartner is not name of a scientist. Okay, Gartner is a research and development firm. The main goal of Gartner is to suggest what are the trending technology based upon the industry. So if you go for this Gartner hype cycle, which was released in 2024, and every year Gartner releases hype cycle 2 times every year, but you will not find the latest hype cycle because you have to buy that particular hype cycle. If you want to be a part of a company, or let's say CEO of a company or CTO, Chief Technical Officer of a company, so you have to buy it, okay, you have to purchase, you have to give subscription, then only you will get the latest hype cycle. So whatever hype cycle I am showing you, it is available in the public domain. So in 2024, in the month of July, just 1 year back, Gartner releases this particular hype cycle that talks about various deep technologies, not deep learning, it is deep technologies. So if you go to this hype cycle, it shows time versus expectation. This is my time and this is with respect to expectations. So over a period of time, what I can expect from a particular technology. Like human being is also having a life period, right? Childhood, adulthood, elders, like that. Similarly, this time is also divided into 5 different parallel axes, starting from innovation trigger. Innovation trigger means when the technology is new to the market. Like now we are crazy to know about what is quantum computing. Maybe after 10 years people know what is quantum computing. It is a general term, right? Then there is a peak period. After the innovation trigger, there is a peak period. then there is a disillusionment period, then slope period, then plateau period. Plateau period means it is absolute. Like if I ask you Nokia 1100 mobile phone, how many of you are having 1100? Very less, right? Because that is a mature technology, everybody know about that particular technology. So one day quantum computing will also lead to this plateau part, right or not? So if I see this one, you can see here there is a yellow color triangle, if it is visible to you, right, which is mentioned as quantum machine learning. So quantum machine learning is given as life period of more than 10 years. That's why whenever you are guiding a thesis or anything, you tell your student to do something related to quantum machine learning. If it is more than 10 years, if they can do some simple work within 2-3 years, that is of more use, right? Similarly, you see other technologies, if you see also peak period, in peak period also yellow color triangle is there, that is called as quantum algorithm. How to develop quantum algorithm, how to convert a traditional algorithm into a quantum algorithm. Like those people who are working in the soft computing field, because soft computing is used in all the branches of engineering, not in computer science. So there is an algorithm called as genetic algorithm. You might know about genetic algorithm, right? Now traditionally this genetic algorithm is present. What people are doing, how to convert this genetic algorithm into quantum based genetic algorithm. The algorithm is not new, algorithm is there. Or you talk about whatever algorithm you know about the algorithm, design analysis of algorithm also. You have studied different algorithms, greedy heuristic, dynamic programming, branch and bound, divide, conquer, many. How you will convert that algorithm into a quantum based algorithm. That field is also having more than 10 years. That's why this hype cycle is usually referred by the industry people. And this hype cycle is prepared by the Gartner by taking interviews of many CEOs, chief executive officers, many CTOs, many software engineers. Based upon that, they have given this life period. Okay, so this is giving you different areas where you can do research work in the field of quantum computing. Now, let us see what are the problems that are not solvable using a computer system for which we are looking for quantum computer. See, somebody wants 2 into 3. Is it required a quantum computer? No. 2 into 3 can be done easily by a CPU. Why you need also new CPU, right? So you should know what kind of problems are suitable for quantum computer. So I have 2 examples for you. First example is a well-known problem in algorithm theory, that is called as a traveling salesman problem. All of you know about TSP problem. What TSP problem do? TSP problem find if there is a source and there is a destination and there are, let's say, n number of cities. So you need to visit all n cities. All city need to be visited once. You cannot skip a city. Okay, with minimum cost. With minimum cost, let's say each distance is given with a cost. That minimum cost you have to do. So this problem is always called as a NP hard problem, right or not? Non-deterministic polynomial hard problem, right? So for NP problem, solutions are exist in exponential manner. I can find a solution, but it will take exponential time. Like if you take a small example, suppose I have let's say 4 different tasks. I want to perform 4 different tasks in 2 different machines. How many ways I can assign these 4 tasks into 2 machines? What is the number? There are 4 tasks I need to assign to 2 machines. How many ways I can assign these tasks to the machines? 16, right? That is called as 2 to the power 4 is 16. 2 to the power 16 is possible in CPU, possible in GPU, possible in QPU. So when there is a possibility, I will choose CPU only because CPU is low cost, right? But instead of this 4, if I take, let's say, number of tasks is, let's say, 512. Instead of this 2, I am taking number of machines as 16. So how many possible ways? 16 to the power 512. So if you type 16 to the power 512 in your mobile phone calculator, can anybody try? 16 to the power 512. If you type in your mobile, then you will not get any output. Forget about 16 to the power 512. If it is 10 to the power 512, then 1 followed by how many zeros? 512 number of zeros. 1 followed by 512 number of zeros. If each solution takes 1 second of time to check how we are going to assign, each solution takes only 1 second of time, you need 16 to the power 512 second time. So this problem cannot be solved in a human being life period. So for such type of problems we can find a solution using QPU. So don't try any type of problem in quantum processing unit. If a problem is not solvable, it is not possible in human lifetime, then only we are looking for a solutions with quantum computer. Okay, so in traveling salesman problem, people usually look into quantum based solutions, and this problem is not a vague problem. Somebody has proposed like this. You see, there is a practical example. So there is a city that is called as Spakagati. Okay, it is in London, UK, right? So you can see here, if you see this junction, it looks like a junction, right? So if you see, this particular picture is having 7 different roads, 2 different railway lines, 3 canals and 2 rivers, which leads to 150 plus number of destinations. 150 plus number of destinations. So if I consider this 150 destinations as one node, finding a path to cover these 150 nodes is challenging. That's why in order to solve this particular problem in algorithm theory, we look for approximation algorithm. What is approximation algorithm? For example, I came from NP-hard problems are solved using approximation algorithm. What is actually approximation algorithm? Approximation algorithm says that, for example, Warangal to Rajahmundry, if I travel, the cost is, let's say, 500 rupees. Okay, optimal cost is 500 rupees. So I can develop a 2 approximation algorithm if the cost is not exceeding 1000 rupees. Best cost is 500. If I multiply 2, then the cost will not exceed 1000 rupees. Then I can claim my algorithm is a 2 approximation algorithm. So somebody can come up with 1.5 approximation algorithm also. So 1.5 approximation is much better compared to a 2 approximation algorithm. Somebody will come as 1.25 approximation algorithm, that is much better than 1.5 approximation problem. So this type of problem is suitable for a programming a quantum computer, because it is not possible with the help of CPU. Now there is another problem which you may be aware, that is called as rice and chessboard story. How many of you know? Okay, what is the story? Tell me. Yeah. So what we are doing here, it is just like a exponential problem, right? So what happened? You can see there is a king and there is a person. Okay, you can see this picture. Okay. Okay, king and there is a person, right? And there is a chessboard, right? So king is impressed. You know, kings are very impressed if you tell something, right? So they are very impressed, right? So king wants to give something. It is also supposed to work, but why it is not working? I don't know. Yes. So you can say there is a chessboard, right? So the inventor of this particular problem, okay, so he showed this game to a king, and king is very impressed to see this particular game. So king wants to reward something to this inventor of this particular game. So what he suggested that there are so many you can say squares, right, in a chessboard. So he told that in every square you put first square you put one grain, right, and in the next box you put 2. Next it will be 4, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6. So that it will be cover the entire chessboard. You know there are 64 locations, right? There are 64 points, right? So if you see the number of grains that is collected by this inventor is this much big number, right? So this problem is growing, right? One it looks very easy, 2, 4, then let's say 2 to the power 3, 2 to the power 4, it looks very simple. But if you add up to 64, it is a very large number. So this inventory is very tricky to tell about a reward, right? So such type of problems needs what? Quantum computer to solve, right? Okay. So in quantum computer we use qubits, okay, instead of bits. So qubits are in short called as qubits, or it is also written QU bits. So in my presentation you can see maximum cases I have written QU, some cases it is qubits, both are same. So bits means either the value is 0 or 1, and classical computer uses this system, either the value is 0 or the value is 1. But when I toss a coin, the value is in between 0, 1 in any state. That is considered a superposition. Superposition means any state in between 0 to 1 is considered a superposition. But once you represent the superposition, as I stated earlier, finally you have to convert to 0, 1 only. Initially you have 0, 1, move to superposition, move superposition to again 0, 1. That is the way you have to write a program in QQ. Okay. So earlier we more rely on the transistors, right? If you see starting from the mainframe computers, although transistors are reduced in the later computer, but now instead of going for the transistor, what we want? We want macro states. Macro is the minimum one, minimum states, right? Minimum number of states to represent a particular thing. That advantages you will get with the help of a quantum computer. We also move from the bit which is used by the conventional system to qubit in the quantum computer. That is also one transition that we are going to perform in quantum computer. And when you deal with a single qubit, we call that as superposition. When you go for multiple qubit, we call that as entanglement. Okay. So instead of having a single state, we have multi-state, so we can do a task parallelly. So multi-state parallelism is supported by quantum computer, that's why it is popular. Now you can see, for a particular problem, if you required 1 billion second, like I mentioned 10 to the power 512 or 16 to the power 512, that much second is required, that can be performed within 100 seconds by the help of a quantum computer by applying multi-state parallelism. Now what are the different areas, right? Because you belongs to different branches, most of you are maybe CS, right? So these are the different areas or use cases where people look into quantum based solutions. It is having quantum chemistry, quantum simulation, quantum communication, quantum algorithm, quantum machine learning. So those who are working in the machine learning also, you directly now focus that how quantum can be integrated. Don't work in the plain area of machine learning, that area is gone, right? Now if you come to the computing domain, you can see here computing, here we have machine learning. So all those problems are solvable using machine learning, that can be done easily by the help of quantum machine learning, right? Like Google Colab, if you take an example where we write normally the code, when I run this AI ML based model into Google Colab, sometimes it is exceeding the quota, so we have to pay for it, right or not? But if that much memory, if I include the superposition term into that, then computation becomes much more faster. That's why quantum computers are referred compared to the conventional computer. Okay, whether you need scheduling algorithm or you need optimization based algorithm, or you talk about pattern matching, or those who are working in the healthcare domain, right, bioinformatics, biology domain, all these cases comes under this quantum machine learning. And you can see there is no hard and fast boundary between one area to another area. That's why sometimes we take help of the physics people, chemistry people whenever we are developing the algorithms as well, right? So these are the different use cases you can find in quantum computer. So it is not a theoretical devices no more, right? Quantum computer exists now, not in the end user level, but it is available. So we should know that how to convert the conventional way of writing a code to a quantum code, right? So I am going to introduce a simulator that is called as QC engine, QC, quantum computing engine. Without installation, just you go to the web interface, there you can write the quantum programming code. I will tell after introducing some gates the theoretical concept I will tell you how to write. Okay, so many people have defined the quantum computing in different way, like physics people way they have defined in their own way, chemistry people they defined another way. Computing, as I said, I am more interested in how faster I can do the computations, right. So quantum physics term, it is the law of underlying quantum computing, right, like they focus on the photon, they focus on the superposition or entanglement, all these are modeled using those people who are interested in the physics, right. Now coming to quantum information theory, how these laws determine our ability to process information, how you are going to process these informations. Those people are working in the information theory, they primarily focus on this part, right. They do not look into the other part, the physicians or the maybe the chemistry people. The viewpoint of each and every people is different with respect to the quantum computer. So the promise of quantum computer, you can see, which I told you earlier, it is not a conventional computer killer. It is not going to kill the conventional computer. It is just like a complement to a conventional computer. Complement means it is additionally doing certain thing which is not possible by the help of quantum computer. That is the difference between a normal computer system and conventional computer system. Those problems are very difficult to solve in the conventional computer. It can be easily solved using the quantum computer, right. And many things which are impossible with these devices, it is possible by the help of quantum computer. But there are several challenges also, right. If I convert 0 1 into superposition state, again superposition to 0 1 state, then communication is involved. Now communication is also going to be changed, right. We have different encryption method, decryption method or encoding decoding method. Now when everything will be represented in superposition state, so anybody can launch a different type of attack. So the way we look into the communication, that is also going to be changed. The security protocols, privacy protocols, whatever we are using, that also need to be changed by the help of quantum computers, right. Okay. So quantum computer in general it is called as a co-processor, right. We say it is a co-processor. CPU is a processor, quantum computer is also having a processor, that is why it is a co-processor. Nobody is going to replace anyone. Now instead of having this GPU is also a co-processor, QPU is also a co-processor, CPU is also a co-processor. So it is possible a system is having all these three type of processing unit. Okay. So if you want to see this simulator, all of you can type in the mobile https://oreally-qc.github.io. So this simulator is hosted in GitHub. So you can just type this one because we need to write the program into that particular link. Okay, https://oreally-qc.github.io. So this site is the site for QC engine. QC engine is a free online tool to write the program in a quantum computer. Okay, the output what you are going to get in this simulator, the same output you are going to get when you write a program in a quantum computer. There is no difference. So once you are habituated with this simulator, same code if you post in a quantum computer, it will also work. Okay. Now this is the framework you will get. If you type in your mobile, you will get a framework like this. Let us understand what is this framework. It is there in GitHub. It is available in GitHub, right? So you can see this is the web interface of QC engine. I will show you in my computer also. Okay. So you can see there is a run program. Once you write the program, if you want to run, you can click this run program. And there are set of examples are also given with this program. Set of program, inbuilt predefined programs are also mentioned in this tool that you can use to understand how quantum computer works. Okay, this is QC engine, but there is another tool is also recently integrated. So you may find multiple option to run your quantum computer, right? But in this lecture we will focus only on the QC engine part. So here I have written some code, and command lines are written with double slash. Okay, in traditional programming language also we use double slash for what? For command line, and these are the codes that is written in the QC engine. Then in the right part, the screen is divided into three parts, where you can see a program circuit. So when you write a program, then you will get a circuit. Like all of you know about electronics gates, OR, AND, NOT, XOR, XNOR. Similarly, quantum circuit is also a gate kind of thing, that you will get that picture here. Okay, and there is a circle notation in order to represent the quantum in a two-dimensional space. So there is a notation that is used, that is called a circle notation. So you will get a circle notation here. Okay, I will tell you about some of the notations, and if you have written any specific output, okay, that output will be displayed here. Okay, so this is a very easy interface, it is not a complex interface, very easy interface to run the quantum programs. See here, I have written some code, right? Don't look into this code, I will tell you the meaning of this code later. Then you can see there is a circuit, it is coming here. You may not understand this circuit now, until unless I will explain about what is the symbols. Then you can see there is a circle notation and there is a output, if output is generated with this program. Now you can see here, this is your output console, this is quantum circuit visualizer, and this is circle notation visualizer. These are the three parts that is present in the QC engine, right? And this is the circuits, right? This is a circuit, quantum circuit, which we are going to program here, right? And through which you will say that how it is representing different, you can say circles. Okay, it is representing in the form of circle notations, right? So one by one I will tell you. Coming to the different gates that are used in the quantum computer. So if you come to this symbol is called as NOT symbol. Okay, if there is a plus sign within the circle and there is a left and right tail, that is considered as quantum NOT gate. Okay, and if you want to write the code for quantum NOT gate in QC engine, all will be start with QC. All these gates will start with QC. So you can see also QC dot NOT. If you write and if you give a parameter, for example, if I am giving the parameter as 1, so NOT gate is changing that 1 to 0, or 0 if I am giving input, it is giving 1. Okay, so all these programs in QC engine we start with QC. QC stands for quantum computer, and NOT gate, it will flip that particular bit. Don't think that whatever is there in the conventional computer, conventional gates, the same gate is appearing here. There are some additional gates are also there, that I will tell you. Now coming to, there is a called as C NOT. Okay, C NOT is used, it is just like a conditional NOT. So if the condition is satisfied, then only you are going to perform the NOT, right? So you can see here, okay, if there is a condition, right, just like we are writing a if else statement or if then statement, if this particular condition is satisfied, then only I am going to perform the NOT. If the condition is not satisfied, this is not going to do anything. And if you want to represent this particular gate, you will write QC dot C NOT. C is conditional NOT, and you will supply a parameter. Is it okay? Now there is another gate that is called as CC NOT. Okay, you can go for as many as number of C's also, right? These are nothing but the different conditions. So for example, here I have two conditions, C1 is a condition, C2 is a condition. So I am checking that whether C1 condition is true or not, then I am checking C2 condition is true or not. When both conditions are satisfied, then only I am performing the NOT. So this is also called as which gate? CC NOT, or it is called as TOEFL. Okay. Okay. So these gate is applicable when you have multiple conditions. Sometimes you may find a lot of conditions. For example, I will say a person is, let's say, having securing marks more than, let's say, 60%. Also, let's say the person is, let's say, belongs to a state of Andhra Pradesh. If both conditions satisfied, then only you perform this thing, right? In that case, when you have associated with multiple conditions, you will use the gate that is called as CC not. TOFF, you write down TOFFOLLI. TOFFOLLI. So CC naught is also called as this gate. So this gate is same as, okay, this gate is same as our conventional NOT gate. Only conventional NOT gate case you are changing 0 to 1 or 1 to 0, but we are additionally putting a constraint. Otherwise there is no difference between the conventional gate and quantum gate, right? For this case only, right? Is it okay, these three symbols? So you will find these symbols in where? In the quantum circuit. I will show you the program with respect to 1 qubit, 2 qubit and multiple qubits also. Now there is an important gate that is called as a Hadamard gate, right? So for superpositions we are using this particular gate, H gate, right? We represent with H within a square. So that is called as Hadamard gate. If you want to write this Hadamard gate in QC engine, you will write QC dot HAD, head. QC dot head. So that will represent a Hadamard gate. I will share the slide, don't worry. You first understand whatever I am telling. Later you can collect the slide from madam. Okay, you can write the code. You want me to maximize, okay? Is it okay? Okay, so if you have 0, okay, assume that you have a 0, right? You have 0, and if you are giving that 0 to a Hadamard gate, right? So what it will generate? It will change that bit into superposition state. Okay, superposition state, right? That state it will represent, right? And again, if I apply another Hadamard gate, then it will be again back to your current state, right? That I will tell you in the program. Okay, this way the Hadamard gate works. So most of the programs you will find there is a gate called as Hadamard gate. So once you take a qubit and you write a qubit, the next operation we normally do is called as Hadamard gate, right? Because using this gate only I can change it to in superposition case. Any question? Yeah, 0 and 1 both will be there. But I can take a qubit, right? For example, I want to only configure 0. Based upon that, 1 is also going to change when we go for superposition, right? So there is another gate that is called as phase. Okay, here you can see there is a phase symbol. This pi symbol is called as phase symbol, right? So in this phase symbol, you can see I have not mentioned what is the degree, right? I am not specifying what is the degree, right? And if you want to write a phase is normally used to change something, right? I will tell you about what is magnitude and what is relative phase. So in this case you can see I am writing quantum computing QC dot phase. I have to mention angle and C, right? You have to specify that how much you want to do movement, right? Maybe 90 degree, maybe 180 degree, maybe 45 degree, okay? Based upon that it is going to change. Okay, and this is specifically for 180. So we write QC dot phase 180 comma C. This is also called as Z. Z means it is 180 degree and S means it is 90 degree, right? So it is QC dot phase 90 comma C. So if you write 90, the relative phase is going to be changed to 90 degree, and if you write 180 degree, the relative phase is rotated to 180 degree. Okay, we will see some more gates. Similarly, you can see the last one, the phase I am rotating to 45 degree, right. Like that way you can decide that what is the phase change you want to perform. Okay, now what you can see here? Here you can see two phase symbol, right? They are connected to each other. Previous slide you have seen there is a phase symbol, right? Here you can see there is two phase that are connected to each other. We call that as a C phase. What C phase is? It is just like a conditional phase. Okay, C1 is a condition, C2 is a conditions, right? Okay, so we represent it by QC dot C phase. It is called as C phase. And instead of having this phase, if I am having a black colored dot like this one, this is a black colored dot, this is another black colored dot, then I call that gate as a CZ gate, CZ gate. Okay, so it also perform 180 degree by based upon two conditions, one is C1, another is C2. Anyhow, you will be habituated with this one once you try different codes. Okay, is it clear up to this, right? There is another two gates which is more important. One is called as read, another is called as write, right? So when you declare initialize a qubit, the first operation you want to do is to write that qubit, right? And later point of time you can read the qubit also. For example, I have a qubit, now I am writing something into qubit, representing the qubit in a superposition state. Then I am again changing it to, let us say, binary bit, and I am reading that binary bit, right. So if you want to read something, you will use a symbol just like a AND gate. All of you know about AND gate, right? The same AND gate you will find here. So for that you need to write QC dot read. Okay, QC dot read will be reading a particular qubit. Okay. Next you can see there is a gate which is, there is a, you can see there is a circle and there is a Y shape. So this is used for writing something. So I can write QC dot write t comma value. So it will be a it is going to write something into the qubit. Okay, read is just like a AND and write is just like this particular symbol. QC dot write t comma value. Okay, there are some other gates, like there is a root, okay, which we call as root NOT. Okay, root NOT is just like if you want to perform, let us say, root NOT, you have to write QC root NOT. I will show you example, otherwise you will not able to understand what is the main meaning of these gates, right. Just I am showing you the symbols, so that this symbol, whenever it appears in the QC engine, you should be familiar with symbols. Then all of you know swap, right. Swap is nothing but changing two bits, right. So for that we are using just like a cross symbol or a symbol like this. So it is exchanging two different bits. But if I want to put a condition, if that condition is satisfied, then only I am going to exchange the bit, then this symbol is used. That is called as QC exchange T1 T2. So if the condition is satisfied, then only I am going to flip the two bits, otherwise I am not going to change. Okay. So these are the symbols you can see in the QC engine. Okay. Just note down the symbols if it is required to you, otherwise you can take this slide and make it easy or use to know about the symbols. Last one I will zoom it, right. That is C swap. C swap means if the condition is satisfied, then only I am going to do the swap operation, otherwise I am not going to perform the swap operation. Okay. If the condition is satisfied, then only we perform the swap, otherwise there is no swap. But compulsorily if you want to do the swap without any condition, you can simply use the swap. Okay, so if you want to write a quantum circuit, you can make use of these symbols based upon your necessity, and you can design a quantum circuit. And these circuits can be designed, or the circular representations can be represented by writing the code in the QC engine. Okay. Now this is more important. It is very rare that the entire code is going to be run in the QPU. Okay, that is only I first told you, right? It is very rare that the entire program will run in the QPU. No program run in the QPU. Program starts running in the CPU only. CPU instruct the QPU to perform the part of the program. That is the way the program actually runs. And QPU runs in a separate clock than CPU. Obviously, if the clock is different, then only you can get faster one, right? If clock is same, the performance is same, right? Next, a typical QPU has its own special random access memory. Like CPU is having a RAM, in QPU is also you have a special RAM that is required for a quantum computer. And you will see, if you want to know that how many qubits we can generate, so different companies have suggested different thing. Like if you go for IBM, all of you know about IBM, right? International Business Machine. So IBM has designed a quantum computer that has how many qubits? 121 qubits. This is the latest development till now. 1121 qubits are there, right? So assume that 1 qubit in in many superposition state. So 1121 means how many states we have? It is very large, right? But you can see the world's largest neutral atom quantum computer system now having 1225 site atomic array. So there are 1225 number of qubits compared to the IBM, right? Compared to IBM, it has more number of qubits. So day by day number of qubits are increasing, right? Huh? In the computer, they are computer only. This one US only, right? See, everything is graded goes to US only, right? You will not find a computer with this much configuration in India, right? So anyhow, the number of qubits we are increasing, but we will habituated with 1 qubit, multiple qubit, so that we can use this qubit. Until unless we not write a program which is making these qubits useful, there is no point of looking into these qubits. Although this qubit is a small number, 1121. The cost is very high. Okay, I cannot tell you the exact cost, but cost of quantum computer is very high. That's why I am saying the alternate way of using this quantum computer is you have to use a cloud service provider like Amazon. Amazon is giving you this the quantum computer. So you can run your quantum program, let's say for 15 minutes, and then there is no need of that quantum computer. But I cannot buy a computer to run. It is in billion. It will be in billion, right? It again depends upon what is the capacity of a quantum computer. Like if you ask what is the cost of a computer, we cannot specify what is the cost of a computer. It's based on the configuration, right?
Does the cloud engines provide programming or simulating?
No, they are providing actual programming, experimentation, not a simulation. What we are going to do, that is simulation. But in cloud case, what you are doing, that is experimentation. Really it happens in the quantum computer.
So they are making it.
Yes. Really it happens. In cloud, you go to deploy a virtual machine or this Google Drive. It is an actual thing, right? You can store it in Google Drive, you can download in any computer. It happens in real life. It is not a simulator. It is an experimentation only. Okay. So I will more focus on the 1 qubit. Be familiar with 1 qubit code. If time permit, I will go for multi-qubit. Otherwise, you make use of this slide. Just instead of having 1 qubit, you have another qubit. You can think about 2 qubit, 3 qubit, 4 qubit, like that, right? Okay. So this we have seen in the conventional system. In the conventional system, when I represent 0, okay, you can see in the conventional system when I represent 0, then 0 is highlighted, 1 is not highlighted. Okay, here black color indicates it is highlighted, right? But if I want to focus on 1, then 1 is set, 0 is reset, right? Set, reset. At a time a bit is either 0 or a bit is 1. Like if I want to represent numeric 2, decimal 2 into binary system, I am writing 1 0, right? 2 in decimal is binary, it is 1 0. So I will use 2 bit, 1 bit will represent this 1 like this, another bit will represent this 1, right? So simultaneously I am using this 1 0. This is there in the conventional system, same it is applicable to quantum computer also. Now what is the new thing here? Whenever you read a value of a qubit, you will always get either 0 or 1. Okay, read always happens at the end of the program, write always happens at the beginning of the program. Okay, for read and write, normally in programming language we read something, right? But in quantum programming, first we write. Why we are writing? We are setting a particular qubit, then at the end of the program we are going to read, right? So when you write, you will do with 0 and 1, when you read also it will be 0 and 1. But characterizing this qubit, if you want to characterize the qubit before readout, before reading, then it is not a black and white just like 0 and 1. It may be present in different state.
Is it the bottom of the approach?
Bottom of the approach means, sir?
From the second module to first module.
No. Execution program same only.
Top down or bottom of the approach?
No, we are following sequential programming only. Line 1, line 2, line 3, like that only. Top down approach only. Top down approach only, right? We are not following bottom up approach, right? So qubit, why I am saying it is not so black and white, it is having more number of states. The reason is that you have superposition of the states, okay, and there are infinite possible of number of possibilities in the superposition for a single qubit. That's why you will get a value rather than it is 0 or 1, right? Now the availability of these extra bits allow us to perform some very powerful computing. See, input output is same for everyone, but for computation we represent it in the form of superpositions, right? If you want to do something, that you have to change into superposition so that computing can be done there, and finally you have to again represent in 0 and 1. See this example, this will give you a clarity. So here we are using a notation that is called as a bracket notation, right? Okay, we represent a direct, what we say that? So we represent it by like this, okay, or we represent it by 1, right? So this is the way we are representing the bit. Now you see what is the equivalent of this symbol in a circular notation, right, or circle notation. For example, if I am writing here 0, this is 0, okay, 0 notation, right? Then you can see 0 is set here, 0 is filled with some color, right? 0 is filled with some color and there is a bar. I will tell you what is the meaning of this bar later, right? Similarly, when I write 1, what 1 indicates? It will set 1, remaining 0 is as it is. So these two are equivalent to what? Our conventional bit. In conventional bit case also 0 1 is there, here also 0 1 is there, just we change these notations, right? Bracket notation, and we set based upon what we are representing. If I am writing 0, then I am making 0 as a filled circle, and when I am representing 1, 1 I am representing as a filled circle, and the remaining circle is blank only. Now if you see these two cases, it is 0.707, okay, I will zoom it so that you can see also.
Very less the font size.
Okay, now it is visible. Okay, 0.707, Okay, 0.7007 is a number in between 0 to 1, right? So I am writing this 0.707 in which notation? 0 circle notation, okay, and 0.707 in 1. So as both values are same, so it is having a 50% probability of 0, 50% probability of a 1. So that's why the area filled with this circle, when you go for circle notation, the area filled here is same as the area filled here, not it is covering 50% of the area. Don't be misunderstood with this 50%, right? It is saying that 50% probability, that maybe it means 0, 50% probability it maybe becomes 1, right? So this way we represent it. I will come to this line. Similarly, if I go for 0.95, then our bracket notation of 0, 0.35 bracket notation of 1. So what it indicates? I am giving more probability to this one, less probability to this one. Like that, how many things you can generate? How many possibilities you can generate? Infinite possibilities. This helps us to run multiple things simultaneously. Okay, that is the reason why QPU is performing faster computation. That's why CPU hand over to the QPU and again recollect the result from the QPU. Right? Is it clear, this one? So you can see the area also filled, it is less compared to this one. So it is 95% or 90, you can say maximum percentage is taken by this one, and there is less space is given to the second one.
Can we consider that as voltage, sir? Can we consider that as voltage?
Instead of saying voltage, it's better to say energy. Okay, we not use the current and voltage term in this quantum computing, rather than we say that it is a energy, right, form of energy.
Sir, 0.95 we will consider and we will leave the 1.
No, I am saying that there is some probability of the zeroth notation and there is some probability of this one. One case I am showing you it's 50-50 probability, another case maybe it is 90-10 or 80-20, something like this. Okay. Okay. So what is the change between these two? If I show you this one and this one, what is the change? You can see that bar which we have had maybe in that 12th o'clock, now it is in the 6th one. Okay, 6 o'clock, right? That is the difference, right? So let us understand what is the meaning of these two. Before going to that, I will tell you what is the main thing behind it. Like here you can see, if you go for a physical qubit, this we are saying a logical qubit, because we want to program, that's why we say logical qubit. You can see there is a single photon source, right? Like sun ray is also considered of that, right? So there is a single source of photon. When it reaches to here, there is a switchable mirror. Okay, now it is connected to, that's a reflective state. Reflective state means it will not able to pass through the switchable mirror. It will not able to pass through the switchable mirror, right? So it will redirect it to another mirror, and that mirror is going to produce one, right? Photon passes to a particular switchable mirror. That switchable mirror is in the reflective mode. Reflective means, suppose sunlight is coming, you are putting a mirror and the sunlight is not going to pass that particular mirror, it will reflect. So it happens and it says that I am present in the state number 1. But instead of having this switchable mirror to connect in the reflective state, if I am present this switchable mirror in the transparent state. Transparent means if sunlight is coming, it passes through that particular glass. Then there is no need of this mirror, you will not reflect to this particular mirror, then you will be present in the 0 state. So this actually shows our binary number system 0 and 1. That's why you can see one object that readily demonstrates quantum superposition in a single photon. Either there is a reflective state or a transport. In transparent case it is 0, reflective case it is 1. But now what we have, instead of that there is a half silvered mirror. What do you mean by half silvered mirror? When sunlight is coming or this light is coming, when I stop it, some part is reflecting and some part is crossing me. So this is called as this half silvered mirror, right? So you can see some ray is going to 0 and some ray is going to 1. So this is the main motivation why they have taken for quantum computing, right? Here you can see 50% of the chance it may go to A, let's say, and 50% of chance it may go to 1, or let's say 70% chance it will go to A, 30% it will go to B. So this way we have a half silver mirror to take care of the photon in a physical qubit. But most of the programming case we use a logical qubit, not a physical qubit. Okay, so when a single individual photon hit this particular surface, it loses its identity. Its identity may be 0 or 1, but now it loses the identity. It may be a new identity with some value in A and some value in B. Yeah.
So in order to get the different probabilities, we change that silver one is.
Yes, that silver, that how much we are protecting and how much we are passing. Based upon that, the probability is going to be calculated. Like you have seen that in nowadays.
Is it variable mirrors or only one mirror?
That depends upon what is that mirror, right? For example, you have seen in car also, we are putting different thin layer, but sometimes the thin layer is passing the light, sometimes it is protecting the light, right? So it depends upon that particular material.
Yes.
The material actually will decide that how much it is going to pass, how much it is going to protect.
What I meant to say is that, so we need multiple states, superpositions.
Yes.
In each state we need one class, or we use the
We need a, that is correct. You are saying that if the material is same, every time the probability will be same. But we consider that this is a physical qubit. But when we go for logical qubit, there is nothing like this, right? We assume that there are variety of things are there. But that is true. If there is a material is there, either it will protect or it will pass, or it will do combination of these two with equal probability, or some probability, right? That is not there in the logical qubit. This is just a example why people have thought of going for logical qubit. Okay, but it is not correct to say that photon is present in both 0 and 1, right? We cannot say that it is present in both 0 state as well as 1 state. With certain probability we can say, right? Okay, so there are two things you can find here which we represent commonly as an amplitude. Okay, so the amplitude is having two important aspects. One is called as magnitude, another is the relative edge. What do you mean by magnitude? If you go to the previous diagrams, so you can see the particular circle is filled with some area, right? That is called as magnitude, right? And that bar, okay, which is pointing here, let's say at 12 o'clock, it is pointing, let's say 6 o'clock, it is called as your relative phase. So together this magnitude and relative phase is called as your amplitude, right? So this will help you to represent in circle notation, right? That's why you can see here I mentioned the magnitude is associated with each path of the photon superposition in an analog to how much photon has spread into each path. Okay, if it is a filled circle, so the remaining part of that particular circle, that indicates that that is reflecting. Okay, if you filled with some area, remaining part what it indicates, that is reflecting, and that area represents, let's say, transparent. But when you go for relative phase, it is between different path in the photon superposition captures the amount by which the photon is delayed on one path relative to the others. Okay, what is the phase? For example, we have seen a phase symbol also, right? We can move this relative phase into different angle using that particular gate. Okay, so these you can see here in magnitude case, magnitude of the amplitude, if you see associated with each value of a qubit that we have seen 0 and 1 is related to the radius of the field in area, right? Whereas relative phase is nothing but a darker line that is present in the circular notation. This way magnitude and relative phase are different from each other. Okay, see this one. Now I have given different circles. Now you determine what is their probability, right? For example, if you go to the first circle, it is representing what? Circle notation 0, right? So suppose I will say that here I am determining whatever probability I have mentioned. These probabilities are associated with 1, not 0. associated with 1. If 0 is filled, what is the probability of 1? 0. If 0 is empty and 1 is filled, 100, because I am only considering 1, I am not considering 0. Then in this case, both are filled, right? So there is a probability of 50%. This case also, it is same as this one, only the relative phase is changed. I am not concentrating on relative phase. So how much area it is covered here, shaded area, that I am calculating, so it is 50%. This case, you can see, if it is visible, slightly it is not filled. It is not completely filled, right? So it is occupying, let's say 90%, then I am saying 10% it is go for 1. So these are the different notations we represent. These are normally represented in the form of probability. You know, sum of the probability is always 1, right? So if it is 90%, it is 10%. If it is 50, it is 50. If it is 0, it is 100. If it is 100, it is 0. So this way we represent a different shaded area. Based upon that, we are calculating probability. And this is a very important statement which says that the area shaded in this 0 notation, 0 circle notation, gets larger. 0 is getting larger. That means what? 1 is decreased. 1 is larger, 0 is decreased. So this way we represent different superpositions. Okay. Now if you come to relative phase, what do you mean by relative phase? Is nothing but that darker line, right? The darker line represent your relative phase. For example, now it is present here. Okay, relative phase, when you apply 45 degree, okay, that phase symbol we have seen, right? Phase symbol we have seen. So there are two things you have. One is 0th notation, another is 1 notation. So when you make, here I am not showing you both bit 0 and 1. I am not showing both bit. I am showing that if a circle is like this, when I apply relative phase, what will happen? But normally it is not a correct notation. Correct notation is that you will show the what is the state for 0, what is the state for 1. Then you apply the phase, show the state of 0, show the state of 1. What I want to actually mean here, so 0 will be present in one state, right? Maybe in some shaded area, maybe some relative phase. 1 is also present in some relative phase and some magnitude. Then suppose I am applying this phase. So I need to display what is the content of 0 and what is the content of 1. Every case, whenever you are applying a gate, right, applying any particular gate in quantum circuit, you have to show both notations 0 and 1, but this picture is not showing that. So normally when we change this relative phase is always affected to 1, not the 0. So you will get as it is circle here, but you will get a different one with respect to 1. Okay, normally relative phase is applied like this. So for example, if I am showing this one only, that's why it says that I am showing you a single qubit, I am not showing both. So when I go for this one, you can see here, okay, now it is in this position. When 45 degree, it will work in which direction? Anti-clockwise direction. This is our clockwise directions, right? This one is anti-clockwise directions. So when I apply 45 degree, it is going to change to 45 degree. Are you getting what I am saying, right? Similarly, when even notation is like this, then 90 degree means it will move 90 degree. Okay, similarly, it will move 180 degree, then 270 degree, right? Then if I make 360 degree phase, it is same as the original one. So based upon the necessity, we are going to apply phase into different circuits. So phase enable us to move the relative phase from 0 degree to 360 degree. Okay, 0 to 360 degree, right? That way we can move to one of these bits. Okay, is it clear? Okay, so if a QPU operations were applied to the rotation of the both circles, then we could always equivalently reconsider the effect of one circle was rotated and making relative rotations is steady in apparent phase. What it says that whenever we represent both state, then only you will come to know that one part is only moving, zero part is not moving. Right? That you will see when we represent like this. So the relative phase is always varied independently with respect to the magnitude. We are not focusing on the magnitude part. What is magnitude part? The shaded area. Shaded area we are not focusing. We are only focusing which one? Relative phase. Like that way we are representing this one. Okay. So let us go for first few QPU operations, okay, which will help you to understand that how to deal with the qubits. So single qubit QPU operation transfer the input operations to the desired output. Initially you will take 0 notation and 1 notation, then you will represent in the qubit, right. So input outputs are the qubits rather than the bits, okay, but finally you will get 0 and 1 only. QPU operation is said to be reversible. Every time whenever you are applying a operation, you should know whether it is reversible or not. What do you mean by reversible? Just like if I am changing into another form, if I am doing the same operation, I will come to my original form, then it is called as reversible, right. For example, somebody can say that 0 degree and 360 degree, right. So 0 degree, 360 degree both are same, right. So I will make a operation of 180 degree, right. I will be present in one state, then again I am performing 180 degree. So I am moving to 360 degree. So it will looks like the same. So if a operations is applied multiple times, every odd even number of times, if it is present in the original state, then that QPU operation is considered as reversible, already irreversible. Like if you go to cryptography, there is a one-way function. There are many one-way functions are there. For example, if I say h is equal to f of x, okay, h is a variable which is taking function of something. But when I am taking x is equal to, okay, let us say f h inverse, okay, you will not able to find it. A practical example, you see our OTP. You are making a transaction, you are getting your OTP. It is a one-way function. Given a OTP, if I ask you it is validated to which transaction, it is not possible. So many operations are there in QPU which is not irreversible. You can perform only one time, right? So some Q operations are irreversible, has no inverse, and some QPU operations are also nowhere related to our conventional bits. That way they are different from each other. Okay, so coming to NOT, right? This is our NOT one, right? NOT gate. Okay, NOT means 0 is going to convert to 1, 1 is going to convert to 0. This way it will work. Now I always told you, when the qubit is given, either qubit is represented in 0th notation or in the 1 notation. So when assume that you are present in this state and you are applying NOT operation, then what will happen? Always you remember, make a table and check that magnitude is changed or relative phase is changed. So when you apply the NOT operation, which one is changed? Magnitude is changed, relative phase is not changed. So you can see here there is some relative phase, the same relative phase is transferred to 1. Let us say it may be in 0 degree, then it will be transferred to 0 degree only, right. If it is let us say in 90 degree, then another it will go for 90 degree. It will change from 0 to 1, okay. In terms of that, relative phase is changing, but it is not changing relative phase position. On the other hand, you can see here when we have 0 and 1 like this. So when we change, I will change it to 1, this one I will change it to 1. Just you change these two, don't change the circle notation. This will be changed to 1, so it will look like this one. I will change this one to 0, so it looks like this one. So NOT gate is changing only the magnitude. Relative phase is also changed in the sense it is transferred, but it's there is no phase change you will find when you apply the NOT gate. Okay, yeah, same thing I have represented here also. Now question arises that whether it is reversible or irreversible. If you are present in this state, if you apply one more time not get, right? If you are present in this state, okay, see here, let us say this is a field circle, I am writing like this, and this is my magnitude, okay. This is my 0 in circular rotation 1. So when I apply not get, what will happen? Okay, so I will write, I told you same thing, I will change, right, to here. So this will be my 1 and this one is my 0. Now you apply not get here, then what you will get? Now what you will get here? It will be changed to again this state. So what I can say? It is reversible or not reversible? Reversible. So like that, for every gate you need to determine whether it is reversible or not reversible. Okay, so we will take a break. Okay, after that we will see some programs, some basic level program only I will tell you.
I run this program, I got this output. Okay, so what about this output, sir?
This is only